All right, so building on that last concept, we have our official definition of what we call an definite integral. Now, an integral, you've heard that word before just briefly, but an integral is a way to describe the exact area under a curve. And a definite integral means that not only are we going to take this curve, but we're going to take this curve on some interval from a to b. So the definite integral of a continuous function on some interval a to b is going to be denoted with this notation. This is brand new notation to you. Okay, we have this little integral sign from the lower bound a to the upper bound b. And this is just f of x, which is the output, times dx. Now what's dx? Dx is your delta x. That's the width of every rectangle. Delta x and dx. And what we say is this. The integral from a to b of f of x dx, that's our new notation, is equal to, now this is going to look familiar, the limit as n approaches infinity, n is the number of rectangles, from I equals 1 to n, these are our subscripts, x sub 1, x sub 2, x sub 3, x sub 4, all the way up to x sub n, of f of x sub I times delta x, the output at x sub I times the width of the rectangle. All right, so this definition should make some sense to you. Okay, now let's keep going. A little bit more about this notation. This right here is called an integral sign. All right, it's like an equal sign, but it's an integral sign, and it measures the area under a curve. The a and the b are referred to as our limits of integration. These are just the endpoints on some interval, but we're going to officially call them the limits of integration. The f, which is the function that we're taking the area under the curve of, is referred to as the integrand. And the process of determining a real number, the exact area under the curve, from a to b, is referred to as evaluating the definite integral. Evaluating the definite integral. All right, most important. We say that this integral from a to b of f of x dx measures the net signed area bounded by y equals f of x and the x-axis on the interval from a to b. So the reason we bring this up, the net signed area, is because now we are going to keep tabs on the fact that if the graph were to dip below the x-axis, then this definition here is taking into consideration that areas below the x-axis are represented as negative areas. And a perfect example of this would be a graph that we're familiar with, that we've seen. Let's just take a look at what this graph is. It's some curve, and we have some interval from a to b, which is a positive area. We have some interval from b to c, which represents a negative area, and then from c to d, which is a positive area. So if we want to represent this as integrals, we say this. The integral from a to b of f of x dx, we have to put the dx in there because the delta x represents the width of every rectangle. F of x is the output. F of x dx, that's a1. All right, it's the integral from a to b, the definite integral from a to b. The definite integral from b to c is f of x dx, and that's going to be negative a sub 2. It's negative because the curve drops below the x-axis. So this integral definition is going to take into consideration that that's negative. And then finally we can say from c to d is f of x dx. The integral from c to d of f of x dx is a sub 3. Okay? So when we now put all this together and we take the definite integral from a to d, we can say that the definite integral from a to d of f of x dx is going to be a1 minus a2 plus a3. And that's going to give me some value. And that value represents the area under the curve.